The sun's surface is a roiling ocean of fire, yet that inferno is merely a lukewarm prelude to the universe's true thermal extremes. We are embarking on a countdown of 50 facts that will completely reshape everything you know about hot and cold. You will discover how a place in space can be colder than the void itself, and how a laboratory on Earth can forge temperatures that rival the Big Bang. How can a planet farther from the sun be hotter than its closest neighbor? What does it feel like to touch a substance so cold it defies gravity? By the end of this journey, your very definition of temperature will be transformed. What single temperature extreme do you think will be the most difficult to comprehend? At the sun's very heart lies a furnace so immense it defies all earthly comparison. This core burns at a staggering 15 million degrees Celsius, a temperature so extreme it makes the sun's surface seem almost cool. The secret to this inferno is a process called nuclear fusion. Deep within the core, the weight of the entire star crushes down with unimaginable pressure. This force squeezes hydrogen atoms together with such violence that they overcome their natural repulsion and fuse, creating new helium atoms. In that moment of creation, a tiny amount of mass is transformed into a colossal burst of pure energy. This is not a simple fire, it is the fundamental engine of a star. Every second, the sun's core fuses 600 million tons of hydrogen into 595 million tons of helium. The missing 5 million tons of mass is converted directly into energy, which then begins its long, slow journey outward, eventually emerging as the light and warmth that sustains our entire world. This relentless, violent reaction is the reason our star shines, a continuous cosmic explosion contained by its own immense gravity. Yet that stellar furnace is only half of the story. For the universe holds a cold so profound it challenges the very meaning of emptiness. Drifting through the cosmos is the Boomerang Nebula, a ghostly cloud of gas that holds the title of the coldest natural place ever discovered. Its temperature is a mere 1 degree above absolute zero, a frigid negative 272 degrees Celsius. This is even colder than the dark, empty space that surrounds it. The secret to this deep freeze lies in the nebula's own death throes. A dying star at its heart is expelling its outer layers at a phenomenal speed, racing outward at over 150,000 kilometers per hour. This is like a cosmic air conditioner on an unimaginable scale. As the gas expands so rapidly, it cools down in the same way a can of spray deodorant feels cold as its contents expand into the air. This refrigeration effect has plunged the Boomerang Nebula to a temperature lower than the background glow left over from the Big Bang. Seen through powerful telescopes, it forms a haunting, symmetrical bow tie shape, a frozen monument to a star's final breath. How can something be colder than nothing? The answer lies in this incredible cosmic expansion, a natural refrigerator operating in the void. While the depths of space hold these ancient extremes of heat and cold, our own planet can produce a thermal flash of staggering violence in the blink of an eye. A single stroke of lightning can superheat the air around it to 30,000 degrees Celsius. That is over 5 times hotter than the surface of the sun. This is not a slow, sustained burn like a star, but an instantaneous, catastrophic explosion of thermal energy. The cause is a phenomenon we encounter every day on a much smaller scale: electrical resistance. When you plug in a toaster, the electrical current faces resistance as it flows through the wire, making the filament heat up and glow. A lightning bolt is that same principle, but operating on a terrifying planetary level. A colossal buildup of electrical charge in a storm cloud seeks the path of least resistance to the ground. As it forces its way through the air, a medium that strongly resists the flow of electricity, the result is an unimaginable release of energy. This sudden, violent heating makes the air itself explode outward. It is this rapid expansion of superheated air that creates the shockwave we hear as thunder. In slow motion, you can see the lightning channel form as a series of staggered steps, each one a miniature explosion that blasts a conductive path through the atmosphere until the main surge of power follows in a blinding, incandescent river of plasma. For a fraction of a second, the air along that channel is transformed into a state of matter found nowhere else on Earth, a searing testament to the raw power contained within a simple thunderstorm. That same lightning strike is a fleeting inferno, but Earth holds a record for sustained, oven-like heat that feels truly alien. Furnace Creek in Death Valley, California, earned its name for a reason. In the summer of 1913, the mercury in a weather station thermometer climbed to a staggering 56.7 degrees Celsius, or 134 degrees Fahrenheit. This remains the highest air temperature ever reliably recorded on the surface of our planet. To understand this kind of heat, you have to grasp the geography of the place. Death Valley is a deep, narrow basin walled in by mountain ranges. The sun bakes the desert floor, and that heat becomes trapped, unable to rise and dissipate easily. It is a natural convection oven on a massive scale. The air itself feels thick and heavy, a physical weight pressing down on you. Common summer heat waves in cities might reach the mid-30s Celsius, which is uncomfortable enough. But Furnace Creek at its peak is over 20 degrees hotter than that. At such temperatures, metal surfaces in direct sun can cause severe burns on contact. The air is so dry that sweat evaporates almost instantly, offering no real cooling relief. This is not merely hot weather, it is an environmental extreme that pushes the very limits of human endurance, a reminder that our own world can produce conditions that feel more like another planet. Our own world can produce scorching temperatures, but the solar system holds a thermal paradox that defies simple logic. The title of hottest planet does not belong to Mercury, the world closest to the Sun. That distinction goes to Venus, a planet shrouded in thick clouds where the surface simmers at a constant 465 degrees Celsius. This is hot enough to melt lead, and it presents a fascinating mystery. Mercury orbits much closer to the Sun, so why is Venus so much hotter? The answer is not the Sun itself, but what hangs in the sky above Venus. The planet is wrapped in an incredibly dense atmosphere, more than 90 times thicker than our own. This atmospheric blanket is almost entirely carbon dioxide, a gas that acts like a one-way heat trap. Sunlight passes through the clouds and heats the surface of Venus. That heat then tries to radiate back out into space as infrared energy, but it cannot escape. The immense layer of carbon dioxide absorbs this infrared radiation, trapping the thermal energy and causing temperatures to soar. This is a runaway greenhouse effect in its most extreme form. On Earth, our own much thinner atmosphere creates a mild and life-giving greenhouse effect. On Venus, the process spun completely out of control, turning the planet into a permanent global furnace. The surface is not just hot, it is uniformly and relentlessly scorching from pole to pole, day and night, a stark warning of how a planet's atmosphere can ultimately dictate its destiny. This concept of ultimate cold finds its final boundary in a temperature known as absolute zero. It is the theoretical bottom of the thermometer, the point where all thermal energy is gone. Absolute zero is defined as negative 273.15 degrees Celsius, or zero on the Kelvin temperature scale. At this impossible temperature, the frantic dance of atoms and molecules would theoretically come to a complete and total standstill. There would be no jiggling, no vibration, no movement at all. This is not just a very cold day, it is the complete and utter absence of heat itself. The laws of thermodynamics, the fundamental rules that govern energy in our universe, state that we can never actually reach this point. It is a limit we can only approach, never touch. The closer you get to absolute zero, the harder it becomes to remove the last tiny whispers of energy from a system. Yet in laboratories around the world, scientists have come breathtakingly close. Using lasers and magnetic fields to slow atoms down, they have created conditions within a few billionths of a degree of that ultimate cold frontier. Think of it like trying to slow a spinning top until it is perfectly, impossibly motionless. You can get it to wobble ever so slightly, but stopping it completely would require an infinite amount of effort. These ultra-cold experiments create states of matter that do not exist anywhere else in the natural universe, allowing us to probe the deepest mysteries of quantum physics. So while we can never truly reach the end of cold, the journey toward it reveals some of the most bizarre and wonderful behaviors of the material world. Even the most violent volcanic eruptions seem almost cool compared to the core of the sun, but their heat is immediate and terrifyingly tangible. A river of molten rock, known as lava, typically flows at temperatures between 700 and 1,200 degrees Celsius. That is hot enough to instantly incinerate any living thing it touches and reduce solid rock to a bubbling, liquid state, but not all lava is the same. Its temperature and behavior are dictated by its hidden recipe. In places like Hawaii, you often find basaltic lava, which is richer in iron and magnesium. This composition allows it to melt at higher temperatures and flow with a surprisingly fluid consistency, almost like hot motor oil, creating fast-moving rivers and spectacular lava falls. In contrast, lava with a higher silica content, like the kind found in the explosive eruptions of Mount St. Helens, is much stickier and more viscous. It oozes slowly, piling up into steep, unstable domes, and its trapped gases can lead to catastrophic explosions. The temperature directly influences this viscosity. Hotter basaltic lava can travel for miles, slowly cooling and forming vast, undulating plains of black rock. Cooler, thicker lava might only crawl a few feet a day, its advancing front constantly cracking and breaking as it hardens from the outside in. Watching a lava flow is to witness the very skin of the planet being remade, a destructive and creative force born from a heat that, while dwarfed by the stars, is powerful enough to reshape continents. You might find a temperature hotter than a planet right here on Earth in a wood-fired pizza oven. These ovens routinely reach over 430 degrees Celsius, which is actually hotter than the average surface temperature on the sunlit side of Mercury. It seems impossible. How can a planet basking in the full glare of the sun be outdone by a culinary appliance? The answer lies not in the heat Mercury receives, but in what it cannot hold. Mercury is a world almost completely naked to space, possessing no real atmosphere to speak of. An atmosphere acts like a blanket, trapping heat and distributing it around a planet. Without that blanket, the surface of Mercury is exposed to the raw vacuum. When sunlight hits the planet, the ground heats up incredibly quickly, but the moment that spot rotates away from the sun, all that accumulated heat radiates straight back out into the void. There is nothing to slow its escape. The result is a world of thermal extremes where the day side can sizzle, yet the night side plummets to a bone-shattering negative 180 degrees Celsius. So while a spot on Mercury can get momentarily very hot, its average temperature is held down by its inability to retain that energy. A well-insulated pizza oven, in contrast, is designed to trap and sustain its intense heat, creating a tiny, localized hotspot that, on average, outpaces the searing plains of the closest planet to our sun. This cosmic irony reveals a profound truth. It is not just your proximity to a fire that matters, but what you wrap around yourself to keep the warmth. That brief moment of stellar death forges something new from the ashes. When a giant star ends its life in a supernova, the event creates a fleeting thermal spike of almost incomprehensible violence. As the star's core collapses inward, the pressure and temperature skyrocket to around 100 billion degrees Celsius. For a single, shattering instant, this makes the core of the supernova the hottest natural place in the entire present-day universe, far surpassing even the core of our sun. This inconceivable heat is the forge of a neutron star. In that catastrophic collapse, protons and electrons are crushed together with such force that they merge, transforming into neutrons and releasing a flood of ghostly particles called neutrinos. The entire core of the star is compressed into an object only about 20 kilometers across, yet containing more mass than our Sun. Imagine crushing a mountain range down to the size of a sugar cube. The energy released in this process is so immense that it blasts the star's outer layers into space in a brilliant, expanding shockwave. We see this from Earth as a supernova outshining its entire host galaxy. This is not just an explosion, it is the violent birth cry of one of the universe's most bizarre objects, a celestial diamond forged in a fire 100 billion degrees hot. This pervasive chill is the ultimate echo of the universe's fiery birth. Every point in the cosmos, including the space you are occupying right now, is gently warmed by a faint, uniform glow. This is the cosmic microwave background, the leftover heat from the Big Bang itself, and it has cooled to a mere 2.7 Kelvin, or negative 270.45 degrees Celsius. It is a ghostly whisper of light that has been traveling for over 13 billion years, stretched and cooled by the expanding universe into the microwave part of the spectrum. Its discovery was one of the greatest accidental breakthroughs in science. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, faint hiss in their antenna, a noise they could not eliminate no matter what they tried, even after cleaning out pigeon nests and droppings. They had inadvertently stumbled upon the afterglow of creation. This uniform background is a cornerstone of the Big Bang theory, a fossilized snapshot of the universe when it was just a hot, dense soup of particles and energy. It is the cooled-down ember of that initial fireball, a thermal fingerprint that proves our universe was not always cold and dark, but began in a state of unimaginable heat and density. That faint cosmic whisper is a memory of universal heat, but our own solar system holds a world that is actively, violently remaking itself. Jupiter's moon Io is a celestial pressure cooker, the most volcanically active body we have ever found. Its lava flows are not merely similar to Earth's, they are often significantly hotter, with temperatures soaring beyond 1,300 degrees Celsius. This is hundreds of degrees hotter than the typical basalt flows on our own planet. Io should be a frozen, inert world, but it is caught in a gravitational tug of war between the massive planet Jupiter and its neighboring moons. This constant, intense pulling stretches and squeezes Io's interior, generating immense friction deep within its rocky body. This process, called tidal heating, cooks the moon from the inside out, powering hundreds of active volcanoes that continuously repave its surface. If you could fly over Io, you would see a landscape painted in surreal yellows and oranges from sulfur deposits, dotted with enormous volcanic calderas and vast, fresh lava lakes that glow with an intense, ferocious heat. Plumes of gas and dust from colossal eruptions can be seen arcing hundreds of kilometers into the thin sky, freezing instantly to form a faint, umbrella-shaped snow of sulfur dioxide. This is not a world cooling down from a long-ago formation, but a dynamic, living hellscape, its skin constantly torn open by the gravitational forces of its giant parent planet. Io stands as a stunning example of how a hidden, internal furnace can transform a small, distant moon into the most explosive place in our entire solar system. Our own bodies are a testament to the delicate balance required for life, maintaining a constant internal warmth of 37 degrees Celsius. This is our personal furnace, a baseline of heat that must be defended against a universe that is overwhelmingly either far hotter or infinitely colder. The mechanisms that keep us at this precise temperature are a marvel of biological engineering. Your heart pumps warm blood from your core to your cooler extremities. Your liver generates heat as it processes fuels, and your muscles contract involuntarily in shivers to produce warmth when you are cold. Even the simple act of digesting a meal stokes your metabolic fire. This stable internal climate is so crucial that even a deviation of just a few degrees can spell disaster. A fever of 40 degrees Celsius can cause confusion and discomfort, while a drop to 35 degrees, a state called hypothermia, leads to sluggish thinking and a dangerous loss of coordination. The window for human survival is shockingly narrow, spanning roughly from about 27 to 43 degrees Celsius for our core temperature. Beyond these fragile limits, our cellular machinery simply shuts down. Proteins, the workhorses of every cell, unravel and denature with too much heat, while cold slows our biochemistry to a fatal standstill. When we contemplate the Sun's multi-million-degree core or the boomerang nebulas near absolute zero chill, it is humbling to realize that our entire existence is confined to this slim sliver of the thermal spectrum. We are fragile, warm-blooded islands in a cosmos of violent extremes. This fragile warmth we call life requires a shield against the Sun's fury, and we have now sent one directly into the inferno. NASA Parker Solar Probe has achieved the seemingly impossible. It has flown through the Sun's outer atmosphere, its corona. To survive this journey, the spacecraft must endure temperatures exceeding 1,400 degrees Celsius. How can any machine withstand such an environment? The answer lies in a technological marvel, a heat shield no thicker than a phone book, yet capable of keeping the probe's instruments at a comfortable room temperature. This shield is not a massive slab of metal, but a sophisticated sandwich of carbon composite foam, topped with a stunning white ceramic coating specifically formulated to reflect as much solar radiation as possible. While the corona itself is a superheated plasma, it is incredibly thin, meaning it does not transfer much heat to an object passing through. The real danger is the direct, unfiltered light from the Sun's surface. The shield is designed to face this onslaught, absorbing a minimal amount of energy and radiating it back out into space as intense heat. The side of the shield facing the Sun glows a cherry red, while just a few feet behind it, in the probe's shadow, the spacecraft enjoys the cold of deep space. Every instrument and solar panel peeks out from behind this protective umbrella, only extending into the sunlight for the brief moments required to take measurements. This mission is not a distant observation, it is a daring plunge into a stellar furnace, giving us our first direct taste of the star that gives us life. Between the blazing inferno of true stars and the cold darkness of planets lies a forgotten class of celestial object. Brown dwarfs are the cosmic in-betweeners, failed stars that never quite gathered enough mass to ignite the sustained nuclear fusion in their cores. Imagine a ball of gas dozens of times more massive than Jupiter, yet not even 1/10 the mass needed to become a proper star. These objects form like stars from collapsing clouds of gas and dust, but their inward crush simply is not powerful enough to trigger the hydrogen fusion that defines a star like our Sun. Instead of shining with the energy of continuous atomic reactions, they merely glow with the residual heat left over from their violent birth. Their temperatures are surprisingly moderate by cosmic standards, ranging from a few hundred degrees to just over 2,000 degrees Celsius. This is far cooler than any true star, yet often hotter than the surfaces of many planets. For a time, they can even host their own weather with clouds of molten iron and silicate rain. You could think of a brown dwarf not as a star that failed, but as a colossal ember slowly cooling in the dark over billions of years, a permanent testament to a fire that never truly began to burn. While the Boomerang Nebula holds the natural record for cold, scientists in a laboratory at MIT have created a chill far deeper. They have cooled a cloud of molecules to just 500 nanokelvin. That is a mere 500 billionths of a degree above absolute zero, making it the coldest known spot in the entire universe. To grasp this scale, imagine the gap between the Sun's core and absolute zero. If that entire range were the height of Mount Everest, this experiment would be a single sheet of paper from the summit. Achieving such an extreme requires more than just a powerful freezer. It demands the precise control of light itself. The technique is called laser cooling. Scientists surround the molecules with carefully tuned lasers that act like a thick, viscous syrup of light. As the particles move, photons from the lasers strike them, each impact slowing them down a tiny bit. It is like running through a downpour where every single raindrop hits you from the front, gradually sapping your momentum until you can barely move. This slows the molecules from thousands of kilometers per hour to just centimeters per second, draining their thermal energy and plunging their temperature to almost nothing. Why create such an extreme cold? At these infinitesimal temperatures, the bizarre rules of quantum mechanics take over. The molecules begin to lose their individual identities and behave as a single, unified wave, a state of matter known as a Bose-Einstein condensate. In this strange quantum soup, scientists can observe interactions and behaviors that are completely impossible to see at normal temperatures. This is not just about breaking a record. It is about using the ultimate cold as a microscope to peer into the fundamental fabric of reality, revealing secrets about how matter and energy behave at the smallest scales imaginable. That ultimate cold reveals the quantum world, but humanity has learned to forge its own miniature star on Earth. A thermonuclear bomb, at the instant of its detonation, creates a fireball with a core temperature exceeding 100 million degrees Celsius. This rivals and even briefly surpasses the immense heat burning at the center of our Sun. The physics behind this cataclysm are a terrifying mirror of stellar processes. It begins with a fission explosion, a standard atomic bomb that acts as a trigger. This initial blast compresses a core of hydrogen isotopes like deuterium and tritium, with such unimaginable force and heat that the nuclei are driven together. They overcome their natural repulsion and fuse just as they do inside a star. In that split second of fusion, a fraction of the mass is converted into a staggering burst of energy, unleashing a firestorm of X-rays and neutrons. Historical footage of these tests shows a sun being born on the horizon, a blinding, rapidly expanding sphere of plasma that consumes everything it touches. The light is so intense it can blind observers from dozens of miles away, and the heat can vaporize entire islands, leaving behind only bubbling lava where solid ground once stood. This is not merely a larger explosion, it is the fundamental power of star formation unleashed in an instant, a destructive power that serves as the most sobering reminder of the thermal forces we have learned to command. Mars presents a daily battle between fire and ice. While its average temperature is a frigid negative 63 degrees Celsius, this number hides an astonishing daily roller coaster. At the equator on a calm summer afternoon, the Martian soil can feel almost pleasant, reaching a peak of around 20 degrees Celsius. This is a temperature you might experience on a comfortable spring day on Earth. But this warmth is a complete illusion, a fleeting gift from a distant sun. As soon as that sun dips below the Martian horizon, all that accumulated heat escapes instantly into the void. The temperature plummets, often crashing down to a brutal negative 73 degrees Celsius before dawn. This is a swing of nearly 100 degrees in just a few hours. The rovers we have sent to the surface are our witnesses to this violent cycle. The Spirit and Opportunity rovers relied on solar power, and their engineering teams had to carefully plan their activities around these extremes, ensuring they had enough energy to survive the long, dangerously cold nights. The thin Martian air, over 100 times less dense than Earth's, is the culprit. It is a pathetic blanket, utterly incapable of trapping thermal energy. There is no gentle evening cool down, only a sudden, precipitous drop into a deep freeze. This is not a world with a climate, but a world with a daily thermal catastrophe. A stark lesson in how an atmosphere does not just provide air to breathe, it provides the essential stability that life requires. The very idea of hot water in the frigid vacuum of space seems like a contradiction. Yet astronomers have discovered vast clouds of water vapor around newborn stars, so hot they reach thousands of degrees. This is not water as we know it, not a liquid simmering in a pot. In the near-perfect vacuum of interstellar space, the pressure is so low that water cannot exist as a liquid at all. Instead, these are trillions upon trillions of individual water molecules whizzing around at phenomenal speeds. Their motion is so frantic, so energetic, that if we could measure their temperature, it would register as a searing inferno. The energy comes from the violent birth of a star nearby. As a protostar ignites, it floods the surrounding cloud of gas and dust with intense radiation. This energy slams into the water molecules, exciting them and sending their temperatures skyrocketing. It is the same principle as heating water on your stove, but without a container and without any pressure to hold the molecules together as a liquid. This superheated steam exists in a strange state, a ghostly, gaseous cloud with the thermal energy of a blast furnace, yet it would feel utterly cold to your hand. There is simply not enough matter in the cloud to transfer that intense heat to anything that touches it. These discoveries reveal that the universe is filled with such thermal paradoxes, places where our everyday definitions of hot and cold begin to break down entirely. One of the most accessible gateways to extreme cold is a swirling, misty liquid found in laboratories and even commercial kitchens. Liquid nitrogen boils at a bone-chilling -196 degrees Celsius, a temperature so far below freezing it turns the very air we breathe into a liquid. This substance is not a rare chemical curiosity, it is a workhorse of modern science. Its primary power is its ability to flash freeze almost anything with astonishing speed. In medical and research facilities, this property is used to preserve biological samples like sperm, eggs, and tissues, putting living cells into a state of suspended animation where all biological activity grinds to a halt. But you do not need a lab coat to see its effects. Chefs use it to create the smoothest, creamiest instant ice cream, freezing the mixture so rapidly that large, gritty ice crystals have no time to form. The most visually stunning demonstrations, however, come from its interaction with everyday objects. A fresh rose, dipped into liquid nitrogen for a few seconds, becomes as brittle as glass. When tapped, it does not bend, it shatters into 1,000 frozen fragments. A rubber ball or a banana undergoes the same dramatic transformation, losing all its flexibility and exploding upon impact. These captivating slow-motion videos reveal a fundamental truth about matter, that intense cold can rob materials of their resilience, making them impossibly fragile. It is a vivid, tangible taste of the universe's deep freeze right here on Earth. Deep beneath your feet lies a planet within our planet, a realm of solid and liquid metal burning at nearly 5,500 degrees Celsius. This is the temperature of the Earth's inner core, a blistering heat that matches the surface of our Sun. We have never drilled anywhere near this deep, so how can we possibly know what is happening over 6,000 kilometers below the surface? The answer comes from listening to the planet itself. When a massive earthquake shakes the globe, it sends powerful vibrations called seismic waves rippling through the entire Earth. Scientists meticulously track the speed and paths of these waves as they travel. The way the waves bend, slow down, or are blocked reveals the composition and state of the deep interior. It is like tapping a giant metal bell and deducing its internal structure from the sound it makes. These seismic studies paint a clear picture of a solid iron inner core, surrounded by a churning ocean of molten iron and nickel in the outer core. This incredible heat is not just a relic of Earth's violent formation. A significant portion is continually generated by the radioactive decay of elements like uranium and thorium deep within the rock. These unstable atoms slowly break down over billions of years, releasing energy that acts as a perpetual furnace. stoking the engine that drives our planet's magnetic field and keeps the continents slowly drifting. Our world is far more than a cold rock. It is a dynamic, heat-powered machine with a heart as fiery as the star we orbit. That common image of space as a uniformly frozen void is dangerously incomplete. An astronaut on a spacewalk just outside the International Space Station faces a brutal paradox. The side of their suit facing the sun is being blasted with intense, unfiltered solar radiation, heating it to a scorching 120 degrees Celsius, hot enough to boil water. Yet, just a few inches away, the side of the suit turned toward the deep blackness of space is simultaneously radiating its heat away, plunging toward a frigid negative 150 degrees Celsius. This is not a gentle gradient, but a violent, simultaneous battle between blistering heat and deep cold. The vacuum itself is the key to this extreme duality. With no air molecules to conduct heat, an object in space does not cool or warm evenly. It simply absorbs radiation on its sunlit side and emits it from its shaded side, creating a staggering thermal split. This is the fundamental engineering nightmare for every satellite and probe ever built. Without careful management, a spacecraft would cook on one side and freeze on the other, its metal skin warping and cracking, its delicate electronics failing within minutes. The solution is a sophisticated ballet of reflective white coatings, insulating blankets, and internal heaters, all working to maintain a stable, room temperature environment inside the craft. Our survival in the cosmos depends on this constant, active defiance of the universe's most contradictory thermal environment. The heart of a modern steel mill houses a man-made star, a blast furnace roaring at 2,300 degrees Celsius. This is a temperature that can vaporize steel and melt rock with ease. Within its refractory brick walls, a carefully orchestrated inferno rages day and night. Iron ore, coke, and limestone are fed into the top, while blisteringly hot air is blasted in from the bottom. The resulting chemical reaction is a violent dance of reduction, stripping oxygen from the iron ore and leaving behind pure, liquid iron that pools at the bottom of the furnace. This molten metal, glowing with a blinding yellow-white intensity, is tapped periodically, flowing out in a river of pure light. Watching this process is like looking into a volcano, a controlled, industrial version of the planet's own molten core. The heat is so intense that it feels like a physical force pressing against your skin, even from a safe distance. The roar is deafening, and the glow is so bright it seems to erase shadows. This is the heat that built our modern world, from skyscrapers to bridges, all forged in a terrestrial furnace that momentarily touches the lower bounds of stellar temperatures. It is a profound reminder that humanity has learned not just to endure extreme heat, but to harness it, creating our own miniature suns here on Earth to reshape the very elements around us. Our own moon presents a daily drama of thermal extremes that makes Mars seem almost stable. For 2 weeks at a time, the lunar surface bakes relentlessly under the unfiltered sun, with ground temperatures soaring to 127 degrees Celsius. That is hot enough to boil water instantly on the dusty regolith. Then, as the landscape rotates into the long lunar night, which also lasts 14 Earth days, all that accumulated heat radiates unimpeded into the blackness of space. The temperature plummets to a staggering negative 173 degrees Celsius, a drop of 300 degrees. This violent swing happens for one simple reason: the moon has no atmosphere. On Earth, our air acts as a protective blanket. It absorbs heat from the sun, distributes it around the planet with winds and ocean currents, and traps enough warmth to prevent the nights from becoming lethally cold. The moon has none of this. Its surface is exposed to the raw vacuum, so it heats like a stone in a bonfire and cools like one tossed into a snowbank. This is why the Apollo astronauts had to carefully time their moonwalks for the lunar morning, when surface conditions were briefly tolerable. Their spacesuits were engineered to reflect the brutal solar radiation and contain their own body heat against the deep cold. Without that technology, a human standing in the lunar daylight would be cooked, while someone caught in the darkness would freeze solid in moments. It is a stark, airless world where the very ground you stand on is either a scorching griddle or a cryogenic plate, a constant reminder of how a thin layer of gas makes our own planet a sanctuary. One of the most mesmerizing demonstrations of extreme cold reveals a liquid that has lost its mind. When helium is chilled below a critical threshold of 2.17 Kelvin, it transforms into a substance that defies every law of classical physics we experience in our daily lives. It becomes a superfluid. At this temperature, just a fraction of a degree above absolute zero, the substance undergoes a quantum identity crisis. All the individual helium atoms lose their individuality and begin to act as a single, unified entity. The most immediate and startling consequence of this is that the liquid loses all viscosity, all internal friction. In a normal fluid, viscosity is the stickiness that makes honey pour slowly and water swirl in a cup before settling. Superfluid helium has zero viscosity. It can flow forever without slowing down. If you were to set a tiny, perfectly smooth whirlpool spinning in a cup of superfluid helium, it would never stop its current circling for all eternity. But the strangeness does not stop there. This frictionless liquid develops an irresistible urge to climb. It forms a film just a few dozen atoms thick that creeps up and over the walls of its container, defying gravity in a quest to find the warmest spot. In laboratory footage, you can watch it silently scale the sides of a beaker, drip from the bottom, and empty the container entirely, leaving it perfectly dry. It seeks out the tiniest cracks and pores, flowing through spaces that would be completely impermeable to any ordinary liquid. This is not a trickle. It is a silent, determined escape artist, a liquid that behaves more like a ghost. How can we possibly explain this? The behavior is a direct manifestation of quantum mechanics, a realm where particles are also waves, acting in concert on a macroscopic scale we can see with our own eyes. It is a stunning glimpse into the rulebook that governs the universe at its most fundamental level, a rulebook where the concepts of friction and containment simply do not apply. The title of the hottest known star does not belong to a brilliant blue giant, but to a dying stellar wolf. In the constellation Sagittarius, a star known as WR102 burns with a ferocious surface temperature of 210,000 degrees Celsius. This is over 35 times hotter than our own sun, a searing, ultraviolet fury so intense it would be invisible to our eyes, radiating most of its energy in wavelengths far beyond what we can see. WR102 is a Wolf-Rayet star, a rare and final phase in the life of the most massive stars in the universe. These are not stable, long-lived suns. They are stellar corpses in the making, having already burned through their primary hydrogen fuel and now fusing heavier elements in a desperate, frantic race against gravity. This furious energy production creates such powerful radiation pressure that it literally blasts the star's own outer layers away into space. Imagine a star so luminous, so violently energetic, that it is continuously tearing itself apart, ejecting its own mass in a colossal stellar wind that streams outward at millions of kilometers per hour. This is not a gentle shedding, it is a constant, explosive loss of material, creating a vast, glowing nebula around the star made of its own scorched remains. A star like this can lose an entire sun's worth of mass in just a few 100,000 years, a mere blink in cosmic time. This dramatic self-destruction leaves behind a bare, exposed stellar core, naked and blistering, which is the source of that unbelievable temperature. This extreme heat also dictates a short and violent future. A Wolf-Rayet star is a ticking time bomb, destined to end its life in a spectacular supernova explosion, or perhaps even a hypernova, a long-duration gamma ray burst so powerful it could sterilize entire galaxies. WR102 and its kind are the universe's ultimate blaze of glory, burning with an incandescent rage before their final, cataclysmic demise. That ghostly fog at a concert or a haunted house has a surprisingly chilly secret. It comes from dry ice, a substance that is actually solid carbon dioxide, frozen solid at a bone-chilling negative 78.5 degrees Celsius. This is so cold that touching it with bare skin can cause severe frostbite in an instant, a freeze far more dangerous than any conventional ice. But its most famous property is the thick, white fog it creates, and that is all about a process called sublimation. Unlike regular ice, which melts into a liquid, dry ice skips the liquid phase entirely. It transforms directly from a solid block into a cloud of invisible carbon dioxide gas. This is why it is called dry ice. It never gets anything wet. To create the iconic fog effect, you simply drop a chunk of dry ice into warm water. The rapid temperature change dramatically speeds up the sublimation process. The invisible carbon dioxide gas billows out, and as it does, it chills the surrounding water vapor in the air, forcing it to condense into a dense, white mist that hugs the ground. For a truly spectacular demonstration, you can seal a small piece of dry ice in a plastic film canister with a little water. The gas builds up pressure inside with nowhere to go until, with a satisfying pop, the lid blows right off. These fun, visual experiments reveal a fundamental principle of matter in action, showing how a substance can leap from one state to another, creating a miniature weather system right on your table. High above our heads, where the sky fades to black, lies a layer of the atmosphere that completely defies our intuition. The thermosphere, a region extending from about 80 kilometers to 600 kilometers up, is officially scorching hot, with temperatures capable of reaching 2,500 degrees Celsius. This sounds like the heart of a blast furnace, a place where any object should instantly vaporize. Yet an astronaut floating in the International Space Station, which orbits within this very layer, would not feel this heat at all. In fact, they would feel a profound and dangerous cold. The secret lies not in the temperature reading, but in the meaning of heat itself. Heat is not just a number on a thermometer, it is the transfer of energy from one thing to another. Down here on the surface, our air is thick with molecules, constantly bumping into us and transferring their energy to our skin. In the thermosphere, however, the solar radiation from the sun is so intense that it gives individual gas molecules enormous speed and energy, which is what the temperature measurement reflects. But these molecules are few and far between, separated by vast distances. There are so few of them that they almost never collide with a spacecraft or a spacesuit. It is the atmospheric equivalent of being in an oven with only a handful of incredibly hot air molecules. You could count the number of molecules hitting you per second on your hands. With so few collisions, almost no thermal energy is actually transferred. The real danger for an object here is not being cooked by hot air, but overheating from direct, unfiltered sunlight on one side, while simultaneously freezing from radiant heat loss into the void on the other. So this region of space, officially one of the hottest places in our planetary system, would in reality feel colder than the darkest polar night. A single comet can embody the universe's thermal extremes in one breathtaking spectacle. As it swings toward the sun, a comet develops two distinct tails, one of blazing light and one of ghostly cold. The first is the dust tail, a brilliant curved stream of countless tiny particles. These specks of rock and ice are blasted from the comet's nucleus by the sun's radiation, and they simply reflect sunlight, shining like a billion microscopic mirrors. This tail glows with the sun's own heat, and the particles within it can be warmed to a significant degree. The second tail is entirely different, an ion tail of ethereal blue gas. This forms when the sun's ultraviolet radiation is so intense it strips electrons from the comet's gases, creating a cloud of charged particles or plasma. This ion tail does not merely reflect light, it is electrified by the solar wind, a stream of particles flowing from the sun, which blows it directly away from the sun in a perfectly straight line. Because this tail is made of such a thin, expanding gas in the vacuum of space, its temperature plummets. The same celestial body hurtling through the void simultaneously displays a warm, dusty trail and a frigid, gaseous one. You can see this duality with your own eyes in photographs of comets like Hale-Bopp, with its clear white dust tail and a sharp, separate blue ion tail streaming in the opposite direction. It is a single object telling two different stories of heat and cold, a beautiful paradox sailing through the solar system. Floating in the outer darkness, Uranus holds a cold so deep it seems to absorb the very idea of warmth. Its cloud tops hold the record for the coldest planetary atmosphere in our solar system, plummeting to a staggering negative 224 degrees Celsius. This is even colder than the more distant Neptune, a fact that presents a fascinating puzzle. Both worlds are gas giants far from the sun's warming rays, so why is Uranus the ultimate icebox? The answer lies in its strange tilt and a missing internal fire. Unlike any other planet, Uranus is tilted so extremely that it essentially rolls around the sun on its side. For a quarter of its long year, one pole is pointed directly at the sun, while the other is cast into a deep, continuous night that lasts for 21 Earth years. You might think the sunlit pole would heat up dramatically, but without a strong internal heat source to churn and distribute that energy, the absorbed warmth seems to just radiate back into space, failing to stir the sluggish atmosphere into a global storm. This lack of internal heat is the second crucial piece of the mystery. Jupiter, Saturn, and Neptune all radiate more heat than they receive from the sun, glowing with the leftover warmth from their violent formation. Uranus, by contrast, is thermally dead. Its core is strangely quiet, offering no supplemental warmth to fight the relentless chill of space. This combination of a sideways spin and a dormant heart has allowed Uranus to settle into a profound, uniform deep freeze, making it the solar system's silent, icy sentinel. A spacecraft returning to Earth must trade the silent cold of the void for a blaze of atmospheric violence. During re-entry, a capsule like the space shuttle slams into the upper atmosphere at over 27,000 kilometers per hour. This is not a gentle glide, it is a catastrophic deceleration. The air in front of the vehicle cannot move out of the way fast enough, so it becomes compressed into an inferno of superheated gas. This process, called ram pressure, generates temperatures exceeding 1,600 degrees Celsius, hot enough to vaporize steel. The craft does not simply get hot, it becomes enveloped in a shroud of incandescent plasma, a fourth state of matter where atoms are torn apart into a soup of charged particles. Iconic footage from the space shuttle era shows this clearly, with the orbiter appearing as a brilliant orange and white star streaking across the sky, trailing a long, glowing tail. This is not fire in the traditional sense. There is no combustion. It is pure, raw energy being released through friction, a man-made meteor intentionally diving home. The plasma sheath is so dense that it blocks radio signals, creating a communications blackout for several tense minutes. The only thing protecting the astronauts inside is a sophisticated heat shield, tiles designed to withstand the blistering temperatures by slowly charring and eroding away, carrying the immense heat with them. This controlled self-destruction is the price of admission back to our world, a minutes-long trial by fire that stands between the tranquility of orbit and the safety of the ground. That fiery plunge back to Earth is a physical inferno, but our own species has engineered a different kind of heat, one you can hold on your tongue. The Carolina Reaper pepper currently holds the official title as the world's hottest, a small, wrinkled fruit that packs a punch far beyond its size. Its heat is measured on the Scoville scale, a system that quantifies the presence of capsaicin, the chemical that tricks your nerve endings into screaming that your mouth is on fire. The Carolina Reaper averages over 1,600,000 Scoville heat units. To put that in perspective, a common jalapeno pepper registers a mere 5,000 units. Eating a Carolina Reaper is not like tasting something warm. It is a full-scale neurological event. Your body's emergency systems are activated as if you have ingested actual poison. The initial bite might be sweet, but within seconds, an intense, building burn spreads across your entire mouth and throat. Your eyes water uncontrollably, your nose runs, and your face flushes a deep red. In online challenge videos, you can see seasoned pepper enthusiasts reduced to coughing, gasping, and sometimes even temporary paralysis, clutching their heads as their bodies rebel against the chemical assault. This is not the thermal energy of a star or a lightning bolt. It is a brilliant evolutionary trick the pepper developed to deter mammals from eating its seeds. The human body, however, has no real defense against this capsaicin invasion except to wait it out, often resorting to dairy products like milk to soothe the burning sensation. It is a self-inflicted culinary hell that proves extreme heat is not always about temperature, but about perception, a chemical fire that burns without a single spark. Deep beneath the crushing weight of continents and oceans, our planet is hiding a startling secret. The Earth's mantle, a colossal layer of rock nearly 3,000 kilometers thick, is not the rigid, solid shell you might imagine. It is a solid that flows. The temperatures here are extreme, climbing from 500 degrees Celsius near the crust to a blistering 4,000 degrees where it meets the core. This intense heat, combined with pressures hundreds of thousands of times greater than our surface atmosphere, transforms the rock into a material that behaves like a plastic over immense timescales. It does not shatter, it does not crack, instead it creeps. Think of it like a glacier, a river of ice that appears solid to the eye, yet flows inexorably downhill over centuries. The mantle moves in the same way, but its currents are driven by the planet's internal fire. This slow, convective churn is the ultimate engine of our world's geology. It is this creeping flow that pushes the tectonic plates apart at mid-ocean ridges, dragging continents across the globe over millions of years. It is this same motion that pulls slabs of ocean floor back down into the depths at subduction zones, recycling the very crust of our planet. This is not a world of static rock, but a dynamic, seething interior where solid stone, given enough time and heat, behaves like a slow-motion ocean, constantly reshaping the face of our world. That fading ember is the long, quiet destiny of our own sun. When a star like ours exhausts its nuclear fuel, it does not vanish in a supernova's glory. Instead, it undergoes a gentle yet profound transformation. It swells into a red giant, its outer layers drifting away into space, leaving behind only its exposed, intensely hot core. This core, no longer powered by fusion, begins a slow and permanent fade. It becomes a white dwarf, a stellar cinder roughly the size of Earth, yet containing nearly all the original mass of a star. The birth of a white dwarf is a spectacularly hot event. Its surface initially blazes at over 100,000 degrees Celsius, shining with a brilliant, piercing white light. But with no internal engine to sustain it, this heat has nowhere to go but out. The white dwarf becomes a cosmic bank account of thermal energy, spending its vast reserves with excruciating slowness across billions of years. It slowly, steadily cools, its color shifting from white to yellow to a dull red, and eventually, over timescales longer than the current age of the universe, to a cold, black lump of carbon and oxygen. This is the ultimate fate of most stars, a gradual dimming into darkness. Our sun, the source of all life on Earth, will one day become a diamond in the void, a silent, cooling monument to the fire that once was. Life in Oymyakon, Russia, demands a resilience most of us can scarcely fathom. This small Siberian town holds the official record for the coldest inhabited place on Earth, with the mercury once plunging to a staggering negative 67.7 degrees Celsius. At such temperatures, the very air becomes a tangible threat. Your eyelashes can freeze together in minutes, and exposed skin risks frostbite in less than 5. The cold is so intense that car engines are left running all day, for turning them off means they may never start again. Residents use heated garages for their vehicles, and they plug their cars into external power sources to keep the engine blocks warm, a common sight in a place where simply going to the grocery store requires meticulous planning. The frozen landscape is both beautiful and brutal, with trees coated so thickly in frost they look like silent, white sentinels, and the breath of every person and animal hangs in the air as a permanent, crystalline cloud. Ordinary tasks become extraordinary challenges. Ink in pens freezes solid, glasses can freeze to your face, and the ground is permanently frozen, making indoor plumbing nearly impossible. Most homes rely on outhouses, a stark reality during the long, dark winters. Yet, a community thrives here, adapting with remarkable ingenuity. Children go to school, but it is only cancelled if the temperature falls below negative 52 degrees Celsius. People bundle in layers of fur and wool, their faces barely visible, moving with a purposeful haste between the warmth of their homes and the few heated public buildings. The people of Oymyakon live in a world of extreme cold that defines every moment of their existence, a daily testament to human endurance at the very edge of our planet's thermal limits. That common flash of lightning is not just bright, it is a contained stellar explosion in our own sky. For a fleeting instant, the air within a lightning channel is heated to 30,000 degrees Celsius, a temperature that truly is 5 times hotter than the surface of our sun. While the sun's surface simmers at a relatively steady 5,500 degrees, a lightning bolt achieves this staggering thermal spike in a fraction of a second. This is the difference between a constant, radiant furnace and a sudden, catastrophic detonation. The sheer power required to superheat a column of air so violently is almost beyond comprehension. Think of the immense energy needed to bring a single pot of water to a boil. Now, imagine channeling that same intensity into a volume of air stretching from the clouds to the ground and heating it to a temperature that would instantly vaporize any known material. This is not a gentle warming, it is a brute force transformation of matter. The air along the bolt's path is not merely heated, it is ripped apart into its constituent atoms, creating a searing plasma state identical to the material of the sun itself. For that brief, brilliant moment, a piece of our own atmosphere touches a temperature normally reserved for the hearts of stars, a dazzling reminder that the universe's most extreme forces are not always light years away. Every record of heat we have encountered so far is a mere flicker compared to the universe's first moment. The Big Bang did not begin with a high temperature, but with an infinite one. This is not just an unimaginably large number, it is a true mathematical infinity, a concept where our current understanding of physics simply stops working. This state is known as the initial singularity, a point of infinite density and temperature where the very concepts of space and time as we know them did not yet exist. The laws that govern our reality, from gravity to quantum mechanics, break down completely at this boundary. We can, however, define an upper limit to temperature, a point beyond which our physical models become meaningless. This is the Planck temperature, approximately 142 nonillion degrees Celsius. That is a 1 followed by 32 zeros. Beyond this staggering threshold, the energy of particles would be so immense that their gravitational force would become as strong as the other fundamental forces, collapsing them into tiny black holes. This was the state of the universe for the first fraction of a second. Then, expansion began. In the first sliver of time, the universe expanded and cooled at a rate that is utterly incomprehensible, dropping from that infinite fever to a mere 10 billion degrees in just 1/millionth of a second. This rapid cooling allowed the fundamental forces of nature to separate out one by one, like layers peeling away, setting the stage for the creation of every particle, every atom, and every star that would ever exist. That initial, impossible heat was not a destructive fire, but the creative forge from which everything we see and are ultimately emerged. Antarctica's East Plateau is Earth's own natural deep freezer, a place so cold it redefines the limits of cold on our planet. Along a high ridge of the ice sheet, satellites have recorded temperatures plunging to -98 degrees Celsius. That is colder than dry ice, and just a whisper away from the lowest temperatures ever recorded on Earth. This extreme chill does not happen on just any frigid night. It requires a perfect and rare set of atmospheric conditions. The air must be exceptionally still and dry for several days, with a complete absence of wind and cloud cover. Under a crystal-clear sky, the icy surface radiates its remaining heat directly out into space, cooling relentlessly without any insulating blanket to trap warmth. The high elevation of the plateau means the air is already thin, holding even less heat to begin with. When all these factors align, the temperature at ground level can drop to a point where the very air feels brittle enough to shatter. Standing there, your breath would freeze instantly into a cloud of ice crystals and fall, tinkling, to the ground. This is not merely winter, it is a near-perfect simulation of the vacuum-like cold found on distant, airless worlds, proving that our own planet can still produce temperatures that push against the absolute limits of physics. Even the deepest cold of space cannot compare to the focused fury of a cosmic blowtorch. Swirling around the invisible point of a black hole is its accretion disk, a vortex of gas and dust spiraling toward oblivion that glows with the heat of millions of degrees. This is not a gentle descent, but a frenzied, chaotic death spiral. As material is pulled inward by the black hole's immense gravity, it does not fall straight in. Instead, it orbits at phenomenal speeds, colliding and grinding against other matter in the disk. The friction from this violent traffic jam is unimaginable, generating colossal heat. This is the same principle as rubbing your hands together to warm them, but amplified to a stellar scale. The gravitational forces at play are so extreme they further compress and superheat this maelstrom, turning it into a seething plasma. Long before any of this material crosses the event horizon, the point of no return, it is torn apart by these forces and screams its existence across the universe. It does not scream in sound, but in high-energy X-ray radiation, a final, brilliant flash of light emitted by matter being heated to its absolute limit. We cannot see the black hole itself, but we can detect this intense, high-energy beacon, the last testament of superheated gas just moments before it vanishes from our reality forever. The universe has been cooling for billions of years, and its single hottest day is permanently behind us. In the very first moments after the Big Bang, the entire cosmos was a searing, uniform soup of energy and particles, a state of almost perfect and unimaginable heat. As the universe expanded, that primordial energy spread out and diluted, its temperature dropping with every passing second. This means the hottest average temperature the universe will ever experience was at its very beginning. Every star that has ever ignited, every supernova that has ever exploded, has only added a tiny, local flicker of warmth to a cosmos that is, on the grandest scale, steadily growing colder. The brilliant galaxies and nebulae we see today are like small, isolated campfires in an ever-expanding, cooling wilderness. This relentless cooling is the ultimate fate of our cosmos, a one-way journey from that initial, infinite furnace toward a state of profound and widespread cold. That same star-like fury is harnessed every day in workshops and construction sites around the world. An electric welding arc burns at a blistering 6,000 degrees Celsius, a temperature that matches the surface of our own sun. This is not a distant cosmic phenomenon, but a controlled man-made star you can hold in your hand, The process creates a brilliant, localized inferno, so intense that it forces metal to melt and fuse together in moments. Watching a welder at work, you see a blindingly bright pinpoint of light, a miniature sun so powerful you cannot look at it directly without protective gear. The welder's mask, with its heavily tinted visor, is not just a precaution, it is a necessity to shield the eyes from the same kind of radiant energy that streams from our star. This is the power of focused electricity, channeled into a tiny gap between a metal rod and a surface, ripping electrons from the air and creating a sustained, searing plasma channel. The sizzling sound and the shower of sparks are the audible and visible evidence of metal being vaporized and superheated, a tiny piece of solar physics operating right here on Earth. It is a profound reminder that the temperatures which forge the cosmos are not always light years away. They are a fundamental tool we use to build our own world. The deep freeze of space is no barrier to liquid water, as Jupiter's moon Europa proves with its own hidden sea. Locked beneath a crust of ice many kilometers thick, a global ocean churns in perpetual darkness. The surface of this world is a fractured, frozen wilderness, one of the smoothest solid surfaces in the solar system, where temperatures never rise above a brutal negative 160 degrees Celsius. At such cold, you would expect any water to be as hard as granite. Yet below this icy carapace, a volume of liquid water twice that of all Earth's oceans may exist. The secret to this profound contradiction is a relentless internal massage. Europa is caught in an orbital dance with the massive planet Jupiter and its neighboring moons. This gravitational tug of war constantly flexes Europa's interior, stretching and squeezing its rocky core. This friction generates immense heat, a process called tidal heating, which acts as a subterranean furnace, preventing the deep ocean from ever freezing solid. This is not a placid, dark lake, but a dynamic global sea, possibly with its own hydrothermal vents on the ocean floor. Wherever we find liquid water, heat, and minerals on Earth, we find life thriving in the most unexpected places. This makes Europa not just a frozen curiosity, but one of the most promising places to look for life beyond our own world. A mission to probe its icy shell and taste the chemistry of its hidden ocean could answer one of humanity's oldest questions. Are we alone in the cosmos, or is life a natural consequence of a universe filled with warmth, even in the coldest of places? Our own planet now holds the record for the hottest temperature ever created. Deep beneath the French-Swiss border, inside the Large Hadron Collider, scientists have forged a fleeting state of matter that has not existed naturally since the first microsecond of the universe. By smashing heavy ions of lead together at nearly the speed of light, they created a fireball with a temperature exceeding 5 trillion degrees Celsius. This is over 350,000 times hotter than the core of our Sun. For a sliver of a second, the protons and neutrons within those atoms ceased to exist. The colossal energy of the collision melted them down into their constituent parts, creating a primordial soup known as quark-gluon plasma. This is the state of all matter in the instant after the Big Bang, a seething, perfect liquid where the fundamental building blocks of reality roamed freely, unconfined. The entire fireball is smaller than a single atom and lasts for less than a trillionth of a second, but its creation allows us to rewind time. We are not just creating extreme heat, we are recreating the very conditions of the universe's birth in a controlled laboratory setting. How do you even measure such an impossible temperature? Scientists do not use a thermometer, they calculate it by meticulously tracking the energy and particles that fly out from the microscopic explosion. This is not merely breaking a record, it is opening a window directly into the first moments of everything, allowing us to stare into the forge of creation itself. Even a humble candle flame contains a universe of temperature extremes. That soft, flickering light is not a single, uniform ball of fire, but a layered thermal structure you can see with your own eyes. At the very base of the flame, nestled just above the wick, is a small, dark blue zone. This area is surprisingly cool, relatively speaking, at around 500 degrees Celsius. Here, wax vapor is just beginning to mix with oxygen, preheating for the main event. Just above this, you find the iconic bright yellow region that we all recognize as the flame. This is the heart of the luminosity where the real combustion happens. Soot particles form in this zone and are heated to incandescence, glowing with that familiar yellow light. This is also the hottest part of the visible flame, reaching temperatures of about 1,200 degrees Celsius, but the true thermal champion is often invisible. A thin, faint outer mantle of blue surrounds the entire yellow flame. This is where the combustion becomes most complete and efficient. The mixture of fuel and air is perfect here, and the temperature can actually climb even higher than the yellow center, but it emits very little visible light, making it a hidden inferno. The entire system is a perfect demonstration of fire chemistry. The wick draws liquid wax upward, the heat vaporizes it, and the resulting gas reacts with oxygen in a delicate, self-sustaining dance. A candle is not just a simple source of light. It is a miniature chemical reactor balancing heat, light, and fuel in a beautiful, layered equilibrium right before our eyes. Far beyond the last planet, in a profound silence untouched by the sun's warmth, lies the solar system's final frontier. This is the Oort cloud, a vast, spherical shell of icy objects enveloping our entire planetary neighborhood. It is so distant that its inner edge is 1,000 times farther from the Sun than Neptune, and its outer boundary stretches nearly a quarter of the way to the next star. Here, in this unimaginable emptiness, the temperature is a mere 4 or 5 degrees above absolute zero, a deep freeze that has persisted for over 4 billion years. This is not just a cold place, it is a cosmic deep freezer, perfectly preserving the pristine building blocks from which our solar system first formed. These icy bodies are time capsules containing dust, rock, and frozen gases that have remained virtually unchanged since the dawn of the Sun. They are the leftover raw materials from the solar system's construction, too far from the center to ever clump together into a planet. Occasionally, the gentle gravitational nudge from a passing star or the collective pull of the galaxy dislodges one of these ancient icebergs, sending it on a million-year fall toward the inner solar system. As it approaches the Sun, its frozen gases heat up and burst into a glorious, streaming tail, and we on Earth look up and call it a comet. So when you see a comet like Hale-Bopp streaking across the night sky, you are not just seeing a beautiful spectacle. You are witnessing a messenger from that unimaginable cold, a piece of our own deepest history thawing briefly in the light of our star. A shooting star is not a star at all, but a lie told by physics. That brilliant, fiery streak across the night sky is not the meteoroid itself burning up. It is the air in front of it being murdered, when a speck of cosmic dust or a small rock, often no larger than a pebble, slams into our atmosphere at 60,000 kilometers per hour. It does not simply push the air aside. It rams into the atmospheric gas with such incredible speed that the air molecules cannot escape. They become compressed into an intensely dense, superheated layer right in front of the falling object. This is the same principle of ram pressure that creates the plasma shield around a re-entering spacecraft, but on a smaller, more common scale. The compression heats the air to a phenomenal 1,600 degrees Celsius, transforming it into a searing plasma that glows with the intense light of stripped atoms. This brilliant envelope of incandescent gas is the fireball we see from the ground, a fleeting atmospheric scar. Meanwhile, the tiny stone or fleck of iron at the center of this maelstrom often remains surprisingly cool for a little while, insulated by its own surface. The heat has not had enough time to conduct inward before the entire object is vaporized or falls to the ground as a cold rock. We are not watching a rock burn, we are watching the atmosphere itself turn into a temporary, miniature star, all for a piece of cosmic debris that may have been drifting in the frozen void for billions of years. Kelt 9b is a gas giant living on the edge of stellar destruction. This planet orbits so ferociously close to its parent star that its dayside temperature soars beyond 4,300 degrees Celsius. That is hotter than the surface of a red dwarf star. Its one complete orbit lasts less than 2 Earth days, a frantic, blistering sprint around a stellar inferno. The star it circles is not a gentle sun like our own, but a blue giant, burning twice as hot and pouring out a torrent of ultraviolet radiation. On the dayside of Kelt 9b, this relentless assault literally cooks the planet's atmosphere. Molecules of hydrogen gas are torn apart, unable to remain stable under the stellar fury. The planet's atmosphere is not merely hot, it is evaporating, streaming away into the void in a vast, comet-like tail of stolen gas. This is a world in the process of being unmade, its very substance boiled off into space by a star that shows no mercy. Astronomers can actually detect this catastrophic loss by observing the planet as it passes behind its star. A faint haze of vaporized metals trails the planet, a spectral signature of its slow disintegration. Kelt 9b is a fleeting cosmic spectacle, a gas giant being vaporized before our eyes, a stark reminder that some worlds are born only to be consumed by their own suns. This quest for ultimate cold has unlocked materials that seem to defy the very laws of electricity. When certain metals and ceramics are chilled to temperatures colder than the Boomerang Nebula, they transform into something called a superconductor. In this state, a remarkable thing happens. All electrical resistance simply vanishes. Think of an ordinary copper wire as a crowded hallway. As electrons try to flow through it, they bump into the atoms of the metal, losing energy as heat. This is electrical resistance, but in a superconductor, that crowded hallway becomes a frictionless superhighway. Once an electric current starts flowing through a superconducting loop, it will continue to circulate forever, never losing any strength, never needing a power source. This is not a theoretical idea, it is a physical reality that requires intense cold to maintain, often using liquid helium to plunge the material to just a few degrees above absolute zero. The applications are as revolutionary as the phenomenon itself. Superconducting magnets are the heart of MRI machines in hospitals, allowing for incredibly detailed images of the human body. They also power the giant particle colliders that smash atoms together. But the true dream, the holy grail of material science, is a room-temperature superconductor. Imagine a world where power lines could carry electricity across continents without losing a single watt of energy to heat. Levitating trains could silently glide on magnetic fields, and our electronic devices would become vastly more powerful without ever overheating. Finding a material that superconducts at everyday temperatures would trigger a technological revolution on the scale of the invention of the transistor, reshaping our entire civilization by harnessing the perfect flow of electricity. The sun's shimmering crown hides a thermal paradox that defies all common sense. Just above its 5,500-degree surface, the outer atmosphere, called the corona, suddenly soars to temperatures exceeding 1,000,000 degrees Celsius. It is as if the air around a candle flame were thousands of times hotter than the fire itself. This baffling inversion has puzzled scientists for decades because heat simply should not flow from a cooler region to a hotter one. The surface of the sun should be the warmest part, with things getting progressively cooler as you move away. Yet the tenuous, wispy corona blazes with an invisible, ultraviolet ferocity. The secret to this solar mystery is not the sun's heat, but its hidden magnetism. The sun is a roiling dynamo of magnetic fields, and these fields are constantly tangling, breaking, and reconnecting in a violent cosmic dance. One leading theory points to countless tiny explosions called nanoflares. These are not the massive solar flares we observe, but trillions of miniature ones, each a magnetic hiccup releasing a burst of energy into the corona. Individually, they are too small to see, but collectively, they could be the constant, invisible stoking of the coronal furnace. Another powerful idea is magnetic reconnection, a process where twisted magnetic field lines snap and realign into a simpler configuration. This sudden rearrangement unleashes a colossal torrent of energy, accelerating particles to near light speeds and superheating the surrounding plasma. It is like stretching a rubber band until it snaps, the stored energy violently released as heat and sound. The Parker Solar Probe is now flying through this very region, tasting the plasma and measuring the magnetic fields to solve this puzzle once and for all. How can something so distant and ethereal be so unimaginably hot? The answer is written in the invisible lines of force that shape our star. Physics has a name for the upper edge of the thermometer, a boundary of heat so extreme it makes a supernova look chilly. This is the Planck temperature, a theoretical maximum of approximately 142 nonillion degrees Celsius. If absolute zero is the basement of cold, this is the ceiling of heat, a state known as absolute hot. At this inconceivable threshold, the energy packed into a single particle would be so immense that its own gravitational force would become as strong as the other fundamental forces. The result would be catastrophic. Each particle would collapse into a microscopic black hole, and our current understanding of physics, the very laws that describe reality, would cease to function. This is not a temperature that exists in the present universe, not even in the heart of the most violent supernova. It was a condition that could only have existed during the first instant of the Big Bang, a fleeting moment when the universe was a single, infinitely dense point. The Planck temperature is not a place we can ever visit or create. It is a fundamental limit written into the fabric of spacetime itself, a warning sign on the cosmic highway that reads, beyond this point, the rules are unknown. Our final fact brings this journey of fire and ice back to our own world, revealing that life itself is one of the universe's ultimate thermal marvels. In the bubbling, acidic pools of Yellowstone National Park, where water simmers at over 90 degrees Celsius, an entire ecosystem thrives. These are not simple organisms barely surviving, but sophisticated microbes called thermophiles, perfectly evolved to call this boiling cauldron home. They build their cellular structures from proteins and enzymes that would instantly unravel in our own bodies, but are uniquely shaped to remain stable and functional only at these searing temperatures. Their existence proves that the chemistry of life is far more flexible and tenacious than we ever imagined. These microscopic pioneers are not alone. They are part of a whole community of extremophiles that flourish in the most hostile places, from the superheated water gushing from deep-sea vents to the frozen lakes of Antarctica. Life did not simply adapt to a narrow, comfortable band of warmth. It infiltrated the edges of the thermal spectrum, pushing into realms we once thought were utterly sterile. As we complete our count of 50 facts, from the trillion-degree forge of the Big Bang to the near-absolute zero of deep space, we are left with a humbling and powerful realization. The universe is a theater of unimaginable thermal violence and profound cold, yet within that vast range, life has found not just a foothold but a home. It is the most extraordinary extreme of all. From the 5 trillion-degree primordial fire of the Large Hadron Collider to the near-silent, ghostly chill of the Oort cloud, we have journeyed across the entire thermal spectrum of existence. The universe is not a place of simple extremes, but a dynamic and violent landscape of temperature, where the very laws of physics bend and warp under the strain of impossible heat and profound cold. We have seen how a planet can be hotter than the world next to the sun, how a liquid can defy gravity, and how a single object can simultaneously blaze with light and shiver with cold. This exploration reveals a cosmos that is far more strange and wondrous than we could have ever imagined from our own temperate little world. So we turn this final question over to you. Which of these 50 facts reshaped your understanding of hot and cold the most? Was it the evaporating atmosphere of Kelt 9, B, the eternal flow of superfluid helium, or the quiet, fading ember of a white dwarf? Let us know in the comments below which cosmic temperature left you in awe. If this journey to the edges of reality captivated you, be sure to subscribe for more deep dives into the universe's greatest mysteries.